Hi everyone. I'm going to run through these slides fairly quickly. I don't think they're too hard to handle, and I'm going to leave plenty of time at the end for questions because that's often useful for this kind of thing. So I'm going to spend some time at the beginning talking about the structure of, very briefly, the cluster end of jobs, and that will be used to motivate the job failures. So I apologize if there are experienced users or staff watching this. This is pretty basic, but I find that quite a few users don't have a good mental model for what's going on in an HPC compute cluster. Of course, they're centered around compute nodes, but what you primarily see is login nodes where you can connect, usually with SSH. And this thing called Slurm schedules access to the compute nodes. And to do that, it has to have a complete description of the job resources, the memory, CPU, time, GPUs, maybe other things that your job requires. And that's primarily because it's guaranteeing exclusive access to those resources while your job is running. So normally we don't overcommit, and that's important for your model of what the cluster is doing. So every scheduler cycle, the scheduler examines all the queued jobs. Actually, it doesn't examine all of them. It examines the jobs in their priority order, and I'll mention priority later. So it starts at the highest priority jobs and continues for a while. It doesn't actually guarantee that it will examine every job every cycle. So if you have a low priority job, there's actually a good chance that it won't be examined all the time. And this can affect how long your job pens. So I was actually watching this for some of my jobs last night and some random user jobs. And the scheduler can, for a low priority job, not even evaluate the job for up to about a minute. Whereas it's constantly launching jobs as jobs complete and resources become available. So from my observation of the scheduler, I've actually got the bullet points in the wrong order here. The primary reason jobs don't run is priority. Once they have a high enough priority to be examined at all, then the secondary reason is whether the resources they want are available right now. And since the scheduler iterates through this priority sorted list of pending jobs, if you have a low priority job, even if it is examined, the scheduler won't have free resources by the time it gets down to that job in the queue. I also need to mention a few words about how priority works and how jobs are billed, because this is really important in understanding why your job may stay in the queue. So we use a mechanism called fair share. There are lots of different aspects to it, lots of different knobs to tweak. But what it boils down to is a way to permit large projects to use large resources while permitting everyone else to use what's left over. Sometimes we actually refer to the leftover part as opportunistic. If you're using a def account, so when you submit the job, you have to specify an account, and if that account begins with def, you're in the opportunistic class. So you're using what's left over after the rack projects. So we judge fair as relative to a usage target. That usage target is the thing that rack projects get, and it's manipulated in subtle ways for the default projects as well. So there's an expected level of resource usage, and that resource usage is a single scalar value, which means it has to incorporate all the different types of resources. So within Slurm, it's referred to as a billing unit, and we have our clusters set up so that on Graham and Cedar, for instance, sort of the most common nodes have a billing unit that encompasses 1 core and 4 gigabytes. It's entirely possible to have jobs that use a lot of billing units. And this may be surprising. So for instance, if you use one core and hundreds of gigabytes of RAM, your billing for that job will be quite high. So if you use 200 gigabytes of RAM, your billing will probably be 50. Well, it sort of depends on how the job is laid out. But that can affect jobs staying in the queue as well. So now some basics about the structure of Slurm jobs, or how Slurm thinks of jobs. And this is mainly for use in interpreting the job records, which is necessary for interpreting things like exit codes and memory and CPU usage. So Slurm uses a kernel feature called cgroups. Cgroups are a way of limiting the set of processes access to CPUs and memory and devices in terms of GPUs as well. This is sort of interesting to me because this is really the hard part of container systems like Singularity or Docker. They additionally also have a namespace cgroup that makes different file systems appear within the container. In Slurm, a job step corresponds with a cgroup across potentially a number of hosts. So for instance, you could, well, normally if you just have a single serial job, you'll see one job step that contains all of your work. But there may be other job steps. So every time you run srun, for instance, within a job, or when you start MPI jobs, this can generate new job steps. And this is sort of a general feature. Most people don't take advantage of it, but it's quite general. So you can have multiple concurrent job steps, for instance, within one job. Because from Slurm's perspective, all that matters is that you have a fixed set of resources, and how you divide those up is up to you. So job steps are sort of like subjobs. Unless you try for concurrency, they tend not to overlap. So if you have a job, for instance, with a number of sruns within it, each of those will be a separate serial, or at least sequential job step. There are some job steps that you didn't ask for. Well, at least one. So in this example, I've run a script which is the simplest possible job. As I recall, this was running hostname. And SACT is the fundamental tool for examining what happened with their job. And in this case, SACT shows me that the job ID consisted of two steps, which are named with the dot something. And it's fabricated job names for those. I could, in fact, have specified my own job names if I wanted to keep them straight. So the .batch job step is the one where I was actually executing within, and .extern is actually added by our Slurm configuration. I think I have some more complicated examples later on. I guess I should also say, so in this example, I'm using SACT with a wrapper that I wrote that just makes the tables look better. So that's why it says swrapper SACT, and then some other parameters. If you don't specify your own -- format, there is a global setting, a default setting, which is available on all Compute Canada machines that includes a lot of other fields, and it winds up being extremely wide, so it'll be unpleasant to read unless you have a very wide terminal. There's also a very valuable tool called seff. It's not actually specialized to Compute Canada and doesn't really provide all the information you'd want, but it does provide a useful summary. So the key part of this is actually, for me at least, the utilization. So as I recall, when I ran this, I did it using Salic rather than sbatch. So Salic is just an interactive version of sbatch. And I kept it open for 3 minutes, And I only ran one compute-intensive thing within it that, as I recall, used about 30 seconds. Yeah, that works out. So that's about 1/6, 30 seconds of 3 minutes. And it used very little memory. So this was a default SALOC, and the defaults use 256, request 256 by default, and I used only 1%. So this is not what you want to see for a real job, because your CPU efficiency should be higher, at least 75%, and your memory efficiency should be at least 75%, maybe higher as well. So seff is really reformatting the SACT output. This is exactly the same information using SACT. It's slightly more complicated to interpret the utilization because you have to subtract the start and end dates, and then divide CPU time raw by that, which is in seconds, and so on. But you can get the same information this way. And our internal accounting uses SACT. So in this case, I use defaults. If you don't request specific resources, you get a very small amount. So by default, you get 1 core for 1 hour and 256 megs. That's really not intended to be usable. It's mainly intended to encourage you to use a real request for the real amount of time that you want. So this is an example of how the defaults might be a problem. So I ran SALOC, and I didn't provide any parameters, so it gave me 1 hour, 1 core, 256 megs. And I have a script called show my cgroup, which just examines the internal kernel parameters and shows me that in this case my job was pinned to core 13, and my memory limit in bytes was 256 megs. So all I did was I ran a program called IO rate, which is just a bandwidth benchmark, a disk, a file system bandwidth benchmark. I told it to try to write 100 gigs in 32 meg chunks, and here it is printing out its incremental progress in doing that, and you see it dies quite promptly. So it managed to write out 384 megs, and then it got killed. And the reason it got killed was because I used too much memory. And that may be surprising because the disk benchmark itself doesn't use much memory. I mean, it uses 32 megs for the buffer, and that's about it. But if I examine the job with SACT, specifically looking at the exit code, you'll see that the .0 step, which is where I was running the IO benchmark, has an exit code of 0:125, which indicates that it was killed because it used too much memory. In this case, the memory was not explicitly used by the program, but implicitly used for caching IO by the kernel. This page cache can be an issue if your job does a lot of IO. And if that's the case, really the only solution is either to change the way you're doing the IO, so it's essentially done slower, or to ask for more memory. So when you're trying to submit a job, you have to come up with these numbers, and it's not so easy to guess what they should be. One simple rule of thumb is just if you run it before on something like a 16 gigabyte desktop, try it with 16 gigs as a job, or perhaps a little more. The key point here is to run it once with a generous set of resources, and then use something like seff or SACT to figure out how much it actually used, and then prune your successive resource requests. And pruning the requests isn't just to be nice to other people on the system, to make your efficiency look good. It actually makes your job penned in the queue for a shorter period of time. Because if you ask for smaller resources, the system will, well, it'll run it faster. Let's just put it that way. I mentioned billing before, and this is an example of how you can examine your billing usage. So with SACT, the appropriate column is alloc trees. So that's Slurm's sort of lingo for the trackable resources that were allocated to the job. So in this case, I have a set of jobs. The middle one was obviously just using the defaults, 256 megs, one node, one CPU. But the other two have non-unitary billing. So in the first case, I asked for quite a lot of memory. So 32 gigs is 8 times our normal per core sort of slice of a node. And so the billing was 8. In other words, I was using 8, the effective equivalent of 8 cores. Internally, we use the frame process equivalent, and it means a unit of both cores and memory bundled together. So in this case, I was using 8 process equivalents, even though I only used one CPU. And that's by virtue of using 8 times the default or the standard amount of memory. In the third example, I used 3 CPUs and only 256 the default amount of memory per CPU, and so I was only billed for 3 processor equivalents. Now I'm going to get back to job failures. So I've mentioned that you can run out of memory, and there are some other failure nodes that I won't really dwell on, like the fact that occasionally a node will die. Those unusual states are reflected in the job state when you look at it in seff or sact. These are specific cases where your application can fail in certain specific ways, and that's reflected in the exit code as well. So a very common one is if you have a C or C++ program or something that's written in C and C++, and you do a malloc to allocate memory, and for some reason the memory allocation returns null. So most commonly this will happen if you're hitting your memory limit. If that happens, and the program doesn't check the pointer that's returned from malloc, you'll receive a segmentation violation. And that's a signal. It's signal 11 in Unix terminology. And that 11 is propagated in the exit code of the job. And there are some other examples here. So segmentation violation can certainly happen for hitting memory limits. SIGBus is another thing that happens sometimes with inappropriate use of pointers. So if you have problems with stack overflow, for instance, you might potentially hit a SIGBus. SIGABort is a system call, sort of a voluntary system call that you sometimes see being called by, for instance, the Fortran runtime. If it notices some sort of terminal problem, like maybe you're opening a file that doesn't exist. Depending on the language runtime in the program, it might call SIGABort. SIGFPE is an interesting one. Our compilers, by default, don't use trapping floating point, which is arguably not an ideal situation. So that when if your program hits something like a denormal or overflow or underflow or divide by 0, these will normally not generate a trap. But if it does, if trapping is turned on, the job will terminate with a SIGFPE. So when you use too much time, Slurm considers that to be a timeout. The job will get killed, obviously. It's also important to note that this is elapsed time. Some people think that we're billing based on resource usage. So they might be surprised that if their job hasn't used very many actual cycles, that it still gets killed at the end of its timeout period. And that's just because timeout is an elapsed time. Slurm only cares about who has control, who is allocated the particular resources during a particular time. It doesn't really care about how the resources are used. It's also useful that if you have a meaningful, significant job that you really don't want to crash due to a timeout, and you know it's nearing its time limit, you can request adjustment of the time limit by opening a ticket. That is emailing support@computecanada.ca. Now, this is very much an exception. Don't do this regularly or we'll stop permitting it. And it's not a way to violate the fair share or the partitions or anything like that. So if your job runs over its time limit, that's still resource usage. You get billed for the actual resource usage. It's not a way of getting free time by any means. So if your job dies, what do? Please read the job log first, the output from your job. It's hard to overemphasize this, but sometimes it's not obvious. The output files your job generates almost certainly contain some sort of comment about why things are dying. Eventually, I mean, if you open a ticket, which is the last step here, eventually we'll figure it out and we'll probably look at those job logs and maybe we can find out why. But it's much better if the job has logs to see what it said. The next step is to look at the job state and exit code. Jobs that get killed from timeout receive a signal that they can, in principle, trap and generate a response to. But they're killed pretty much immediately. So the job state and exit code are mostly for unexpected deaths of jobs, such as a node dying or running out of memory. Seff is really valuable for this because the percent utilization, I mean, we like to say that you should have good utilization, but if your utilization is 100%, then the chances are very good that something bad happened. So if you use exactly as much time as you requested, chances are your program didn't finish. Similarly, if you use exactly as much memory as requested, it's entirely possible that your program died by hitting the memory limit or was killed when it tried to allocate too much. And if none of that works, certainly open a ticket. We have lots of very expert staff who can look at these things.